Hello students, my name is Shubham. I am the Faculty of Physics at MidhaGuru. And today we are going to discuss an interesting chapter of physics, that is calorimetry. In this chapter, we will study about heat, heat transfer and the associated concepts such as specific heat capacity and heat capacity. So now let us start the chapter. First, we are going to talk about heat. And in heat, we will first understand at atomic level what it is. And for that, we need to understand what is internal energy. Now, in layman terms, if I say, then internal energy is basically the sum of the energy exhibited by an atom or a molecule. In simple terms, you can say so that it is the sum of the total kinetic energy and the potential energy of an atom or a molecule. Next, we have thermal energy. So what is thermal energy? Thermal energy is the sum of the internal energies of all the atoms or molecules in a given mass. Next, heat. We generally confuse thermal energy with heat, but there is very slight difference between these two, although they are similar. Now, here it is clearly written that energy which flows from a hot body to a cold body on keeping them in contact is called heat energy. And the SI unit of heat energy, as we all know that it is a form of energy, will be joule. But specifically for heat, we have another unit which is used more commonly, and that is called calorie. And in fact, here it is also given that a common unit of heat is calorie. Next, we need to understand the relationship between calorie and joule. So, 1 calorie is approximately equal to 4.2 joules. Now, joule is a very smaller unit, and in fact, in the same way, calorie is also a smaller unit, and it may have very little practical significance for us. And that is why we define a higher unit of energy, heat energy to be precise, that is kilocalorie. Now, we know that 1 kilocalorie is equal to 1000 calorie. And here it is clearly given that 1 calorie is 4.2 joules. So we can write that 1 kilocalorie will be equal to 4200 joules approximately. Right? Now, temperature. Another important thing that we need to understand in calorimetry is temperature. Temperature is a parameter that actually tells us the amount of thermal energy present in any body. And in fact, in more general terms, you can say that it tells us whether an object is relatively hot or relatively cold compared to another body. Temperature as given, it determines the state of the flow of heat, or in other words, it determines the direction of flow of heat. You can say that if an object is at a higher temperature and another object is at a lower temperature, then the direction of flow of heat will be from the object with higher temperature to an object with a lower temperature. Now, it is also written two bodies are at the same temperature. It does not mean that they have the same amount of thermal energy. Now, it is very important, and most of the students who study calorimetry, they forget about this thing. The meaning of this statement is that if, let's say, you have two objects, let's say I have a copper vessel and I have water, and I heat them up to the same temperature, and let us say the final temperature of both the objects is 50 degrees Celsius. Now the question is, which of these two will have more heat energy in it? Or in other words, more thermal energy in it? Precisely, the answer will be water. It takes lesser amount of energy from our end. We have to supply a lesser amount of energy to heat up copper from, let's say, 15 degrees Celsius to 50 degrees Celsius as compared to water from 15 degree to 50 degree. In fact, I'll have to supply somewhere around 5 times more energy to water to heat up to a temperature of 50 degrees Celsius. Now, let's talk about the SI unit of temperature. The SI unit of temperature is Kelvin, and its symbol is capital K. I have a question for you guys. Can you tell me in the comment section that for some parameters, let's say for some measurements or for some physical quantities, the SI unit has a symbol which is a capital letter, like in this case, Kelvin. And for some physical quantities, we have parameters, we have symbols which is not a capital letter. For example, if I talk about speed, the SI unit is written as ms raised to the power of -1. Both m and s are small. Please tell me in the comment section why this is so. Let us move forward. Now, Kelvin is not a common unit to measure temperature. In fact, in our daily lives, we never use Kelvin. So, a more common unit of temperature is degrees Celsius. And there is a direct relationship between degrees Celsius and Kelvin scale. And the relationship is temperature in Kelvin is nothing but 273.15 plus temperature in degrees Celsius. For example, if let us say we have 15 degrees Celsius. Now, what will this look like in Kelvin scale? So, we only need to add 273.15 and that will give us the answer. So, 273.15 plus 15, this gives us 288.15 Kelvin. And due to this reason, we can say that the change in degrees Celsius is same as the change in Kelvin. And here it is written that delta T degrees Celsius is equal to delta T Kelvin. Next, factors that affect heat absorption by a body. There are multiple factors on which the amount of heat absorbed by a body depends. First one is the mass of the body, and it is quite relatable. If let's say you have 100 grams of water and you want to heat it, we definitely know that we'll have to supply a lesser amount of heat. And if I want to heat up, let's say 10 kgs of water, then the amount of energy, heat energy required will be much large. And hence I can say that heat energy Q supplied is directly proportional to the mass of the body. Next, we have the increase in the temperature of the body. The next factor that affects the amount of heat absorbed is the temperature of the body. As the temperature increases, the amount of heat in the body starts to increase. And that is why we can say that heat absorbed by the body is directly proportional to the change in temperature. If let us say I want to increase the temperature by 5 degrees Celsius, then I might require, let's say 1000 joules of heat energy. But if I want to increase the temperature of the body by let's say 20 degrees Celsius, then the amount of heat required to increase the temperature by this much amount will be much larger than 1000 joules. And the third factor that affects the amount of heat absorbed is the material of the body. This factor actually reflects the type of material of the body. If it is a metal, we know that it needs actually lesser amount of energy to increase the temperature compared to some other materials such as water or glass. Let us move forward. Now, if we try to summarize the discussion of the previous slide, then we can say that heat energy Q is directly proportional to M and heat energy Q is directly proportional to the change in temperature. So if I write it in a simple terms, then I can say that heat energy is proportional to mass times the change in temperature. Now if I include a constant of proportionality, which in this case will be C, then I can write that heat energy is equal to C times M times delta T. Now what is this C? This C is the specific heat capacity of a substance, and this is actually a fundamental characteristics of matter. In fact, using a specific heat capacity, we can differentiate between different matters. Next, we are going to understand heat capacity. Now, heat capacity of a body is the amount of heat energy required to raise its temperature by 1 degree Celsius or 1 Kelvin. In simple terms, if let's say you have an object and you want to increase its temperature from 15 degrees Celsius to let's say 16 degrees Celsius, then what is the amount of heat that you will have to supply in order to increase the temperature? That amount of heat is called the heat capacity of the substance. Now here one thing that is very important to note is that we are not talking about the amount or let's say the mass of the body. We are only interested in finding out if let's say I have a body, no matter what is the mass, then what is the amount of heat that I need to supply to increase its temperature by 1 degree Celsius. In fact, there is one more precise definition of heat capacity, and that states that if let's say you have water and you want to increase its temperature from 14.5 degrees Celsius to 15.5 degrees Celsius, then the amount of heat that is supplied to do so is called the heat capacity of the substance, of the water. And the mathematical formulation of thermal capacity or heat capacity is given here. That is C dash, which is the symbol of heat capacity, is nothing but the amount of energy supplied divided by the rise in temperature. That is Q upon delta T. The SI unit of heat capacity is Joule per Kelvin. Now, another more common unit of heat capacity is Joule per degree Celsius or calorie per degree Celsius. Now here I have a question for you guys. It says heat capacity of a vessel is 30 Joule per Kelvin. What does this mean? In fact, the meaning of this statement is very simple. Heat capacity of a vessel is 30 Joule per Kelvin. It tells us that I need to supply 30 joules of heat energy to increase the temperature of the body, or in this case, the vessel, by 1 Kelvin. Next, we are going to talk about specific heat capacity. Now, specific heat capacity is the heat capacity of a unit mass of a substance. Now, you see the difference between heat capacity and specific heat capacity. In heat capacity, we were only talking about the amount of heat supplied to raise the temperature by 1 degree Celsius. We were not concerned about the mass of the body. But in a specific heat capacity, we are talking about the fact that what is the amount of heat supplied to increase the temperature of a body of unit mass. And the SI unit of mass we all know is kilogram. So we are talking about the amount of heat supplied to increase the temperature of a body of mass 1 kg by 1 degree Celsius or 1 Kelvin. The mathematical formulation of a specific heat capacity is given here, and it is denoted by the symbol small c, and it is simply written as Q divided by m times delta T, where Q is the amount of heat energy supplied, m is the mass of the body, and delta T is the change in temperature. Now, since we have already seen the heat capacity and we know that heat capacity C dash is nothing but Q divided by delta T, I can clearly substitute this Q divided by delta T with C dash, and I'll get a new formula of heat capacity, specific heat capacity, that will be C, small c, will be equal to C dash by m. Now, we will understand another thing. From this relationship, that is specific heat capacity equals to Q by m times delta T, we can actually find out the mathematical formulation of the amount of heat energy supplied to a body, or the amount of heat energy that should be supplied to a body to increase its temperature by certain amount. And this can be rewritten as Q is equals to C times m times delta T. Next, from the previous equation, we can actually say that the amount of heat energy supplied to a body actually depends on 3 factors. First is the mass of the body, which is evident from this relationship, that is Q is directly proportional to m. Next is the change in the temperature of the body, and third is the specific heat capacity. Next, we are going to understand that how we will identify that if a substance is a good conductor of heat or a bad conductor of heat, just by looking at the specific heat capacity of the material. Now, if it is a good conductor of heat, then it means that it would have low specific heat capacity. In other words, the amount of heat supplied to a body is less. Then we say that that object is a good conductor of heat. And if the amount of heat supplied to a body of unit mass is very high, then we say that it is a bad conductor of heat. Upon heating, the substance with a lower heat capacity shows a rapid increase in the temperature. If let's say I have copper, for example, and if I heat it, the temperature of copper rises very quickly. But if I, let's say, want to increase the temperature of water to the same level, then I'll have to heat it for a longer time period. Now here it is given that a calorimeter is a cylindrical vessel which is used to measure the amount of heat gained or lost by a body when it is mixed with another body. In fact, let's say you have a liquid A whose temperature is already known, and you have a liquid B, and you want to find out the temperature of the mixture when these two are mixed together. This thing can be done effectively using a calorimeter. In order to make the calorimeter, as you can see here, I have a calorimeter, a simple diagram of calorimeter, I would say. Now, this calorimeter actually contains a vessel. I have highlighted it with the red ink. This vessel actually is made up of copper, and there are two reasons why we make it using copper. First, it is a good conductor of heat, and second, it has low specific heat capacity. Low specific heat capacity actually ensures that the heat lost to the vessel from the liquid that is kept inside the vessel is minimum, and the measurements that we get from the calorimeter are as accurate as possible. Next, if we talk about the inner and outer surface of this vessel, this copper vessel, then this is polished. And there is a very specific reason why we polish it. We know that heat energy transfer takes place actually using in three different ways. First is conduction, convection, and the last one is radiation. Now, polishing the surface of the vessel actually ensures that the heat is not lost to the surrounding by the method of radiation. Now, for insulation, as you can see, if I go backward, for insulation, you can see that this copper vessel is actually kept inside another basket, or you can say jacket. This jacket is made up of wood, which provides further insulation, and the gap between this vessel and this jacket is filled with a poor conductor of heat, or you can say an insulating material, for example, wool. This region is actually filled up with wool. Now, if I talk about the lid, then lid is also made up of wood, because we know that it is a poor conductor of heat, but it has two holes in it. First hole is this one and second hole is this one. Now, first hole is made to insert the stirrer so that when the two liquids are mixed, we can stir it thoroughly. And second hole is to insert the thermometer so that we can measure the temperature of the mixture. Next, if we talk about the principle, then the calorimeter works on the principle of the methods of mixtures. This principle is also called the principle of calorimetry, and in fact this principle is based on the law of conservation of energy. I think you guys know that what law of conservation of energy states. Now, according to this principle, that means the principle of calorimetry, it states that the amount of heat lost by a body is equal to the amount of heat gained by another body. The mathematical formulation is given here. Heat energy lost by a hot body is equal to heat energy gained by a cold body. Now, let us see the mathematical formulation, like what mathematical formulation we can derive for the calorimeter. So, let us assume that we have a substance A of mass m1, and it has a specific heat capacity of C1, and this substance A is actually at a higher temperature, and the temperature is T1. And it has to be mixed with another substance which has a mass of m2, has a specific heat capacity of C2, and has a lower temperature T2. So clearly, one thing that we can draw an insight from this data that is given to us here is that T1 is greater than T2, and these two liquids are mixed. And we know that when two liquids will be mixed, or let's say when two substances are mixed in general, then the heat transfer takes place from a hotter body to a colder body. And now, if let us say, let us say the temperature T1 is this and temperature T2 is this. When these two liquids are mixed, then the temperature of the first liquid, that is liquid A, which is given here, will start to decrease, and the temperature of liquid B will start to increase, and they will become equal at a certain level. That temperature is given to us here as T. Now, the insight again that can be drawn from here is that T1 is greater than T and T2 is less than T. Again, it is very easy to understand. You see, T1 was here, T2 was here, and T was somewhere in between these two temperatures, right? So clearly, if let us say this is my T, then T1 is greater than T and T2 is less than T. Okay? Now, if I talk about the amount of heat energy that is transferred from liquid A to liquid B, because that is going to happen actually. You see, when I mix two liquids, one is hotter and another one is cold, then the heat energy will get transferred from hotter body to cold body, and there will be a change in temperature for both the liquids. So first, if I talk about change in the temperature, of A upon mixing, it will be how much? It will be T1 minus T. Then I can say change in the temperature of B will be how much? It will be T minus T2. Okay? Now, let us move forward. So now I know that the change in temperature is for liquid A is T1 minus T and for liquid B is T minus T2. Now let us find out how much heat energy is transferred. Now according to the principle of calorimetry, I know that the heat energy lost by A should be equal to heat energy lost by B, given that if I make an assumption that the total heat energy lost by A is transferred to B, which is in practical scenario, it is not always true, because some heat is always lost into the environment. If let us say it is not lost to the environment, then it will be lost at least to the calorimeter, because calorimeter is made up of copper, right? We saw it at the start of our discussion. And if it is made up of copper, then it will also absorb some heat. But for now, we are ignoring that fact. We are only considering the liquids. So now let us see. So heat energy lost by A, it will be how much? We know that heat energy has a formula of Cm delta T. So for A, specific heat capacity was C1, mass was M1, and change in temperature was T1 minus T. Next, heat energy gained, because B was at a lower temperature, liquid B was at a lower temperature. So heat energy gained by B will be equal to C2 times M2 times T minus T2. Now if I make an assumption that the total energy, heat energy lost by A gets absorbed by B, upon assuming that total energy lost by A is absorbed by B, then what can I write? I can write that C1 M1 T1 minus T is equals to C2 M2 T minus T2. Okay, now let us take into picture the calorimeter itself. We know that calorimeter is made up of copper. Okay, and if I want that how much heat, if I want to find out that how much heat is lost to the system, that means to the calorimeter, then I need to take into consideration the copper vessel itself. So if we further assume that the initial temperature of copper vessel is T2. Now you might be wondering why I am saying that the initial temperature of copper vessel is T2, because T2 was the temperature already assigned to liquid B. So you see here, what is the scenario? The scenario is that the liquid B is already present in the calorimeter. Now since it is already present in the calorimeter, then the temperature of the liquid B and the temperature of the copper vessel inside the calorimeter has to be same. They will be at the same temperature, and that is why the temperature of calorimeter, or in simple terms the copper vessel, is T2. Now initial temperature of copper vessel is given to us as T2. Let us say the mass is M3 and its a specific heat capacity is C3. So next, what can I say? I can say that heat absorbed by the calorimeter, or you can say by the copper vessel, it will be how much? It will be C3 M3 T minus T2. And now you see, the only substance which is losing heat in this system, in the example that we have taken, is liquid A. And there are two substances which are actually gaining, or let's say absorbing the heat. First is liquid B and another one is the calorimeter itself. So I can say now that C1 M1 T1 minus T should be equal to, this is the total heat energy lost by liquid A, and it should be equal to the heat energy absorbed by liquid B plus the heat energy absorbed by the calorimeter. So it will be C2 M2 T minus T2 plus C3 M3 T minus T2. This can be simplified further and it becomes C1m1 T1 minus T equals to T minus T2 times C2m2 plus C3m3. Okay, so this was the mathematical formulation from the calorimeter. Now this concept that we have right now discussed is very important. Specifically, a lot of numerical questions are asked in the examination related to this concept. Okay, so do not forget to solve as many questions from this concept as you can. Now we are going to understand the uses of specific heat capacity. First is moderation of climate near the seashore. We already know about the land breeze and sea breeze, and this is possible because there is a difference in the specific heat capacity of seawater and the land. In fact, the specific heat capacity of land is much lower compared to seawater, and this gives rise to the sea breeze and land breeze. Next, the use is in fermentation using hot water bottles. Now, what is fermentation? In fact, you might have used it. We have hot water bags which is used to ease out the pain. Let's say if you have abdominal pain or some pain in some muscle sprain, for example, then we use hot water bottles, and that relieves the pain actually. So relieving the pain using hot water bottles or using warm water is called fermentation. And this fermentation is possible because of the higher specific heat capacity of water. Due to the higher specific heat capacity of water, it remains hot for a longer time period and it helps in relieving the pain. Next, it acts as an effective coolant. Now we know that the specific heat capacity of water is very high, so in order to increase the temperature of water by a significant amount, it has to absorb a large amount of heat. Now if I want to cool a substance which has a very low specific heat capacity, then the water will absorb heat, but the temperature of water itself will not rise by a significant amount, but the temperature of the substance which we are trying to cool will decrease by a significant amount. Next, it is used as a heat reservoir for wine and juice bottles to avoid freezing, protection of the crops from frost, and regulating body temperature in plants and animals. Next, let us understand the uses of heat capacity. You need to understand, in this slide we were talking about the uses of specific heat capacity, not heat capacity. Now we will understand the use of heat capacity. So you see, cooking utensils, if you have seen it, let's say pressure cooker or the pan in which we fry vegetables, they have thick bases. But there are again some utensils which have thin bases. Now what is the principle behind it? Have you seen tawa, that tawa on which we prepare chapatis, we cook chapatis? That is very thick. The base of the tawa is very thick. What is the reason behind it? We know that if I have, for example, a thick base, that means if I have a thick layer of metal, then it means that I will need more heat to increase the temperature of that utensil. Okay. Now due to this, what happens? The utensil itself does not get heated up quickly and the cooking becomes even. Now the base of electric iron is made thick. Again, the principle is the same. If it has a thick base, then it will heat up slowly, but once it has been heated up to a certain temperature, then it will not lose its heat immediately. In fact, even if the current is gone, the base of the iron, you might have seen it also, you might have observed it also, that the base of the iron remains hot for quite some time. Now, the vessel used for measuring the heat of the substance placed in it is made thin. In fact, this point is actually talking about the calorimeter, which we have seen in the previous slides. And the copper vessel that we used is very thin, because we do not want that lot of heat from the liquids that are placed inside the calorimeter is lost to the calorimeter itself. And hence, if we keep the vessel thin, then the heat lost to the vessel will be much less. Now, let's talk about change of phase. Now, in fact, you have already studied these things in the previous classes also. Basically, there are different phase changes. First is melting. What is melting? It is a phenomena in which solid gets converted into liquid. Then we have freezing, just the opposite of melting, in which liquid gets converted into solid. Then we have vaporization. In this, the liquid gets transformed into gas. Then we have condensation, which is the opposite of vaporization. In this, gas gets converted back into liquid. Then we have solidification, when a gas directly gets converted into solid. For example, if we have camphor, then it sublimes actually. Okay, it gets converted from solid directly to gas and then from gas directly to solid. Next we have sublimation, that is when a solid changes directly into gas. Now we will understand these concepts one by one. First, let us understand freezing, or you can say melting, because these are related, you see. If I talk about freezing, it means change of liquid to solid, change from liquid to solid. If I'm talking about melting, then solid to liquid. Now here it is given, the change from solid to liquid phase by absorption of heat at a constant temperature is called melting. The precise definition of melting says that it happens at a constant temperature, and when a solid is melting, is getting transformed into liquid, at that point of time, the temperature of that system, I would say, where you have some part is solid, some part is liquid, when the transformation, when the phase change is actually taking place, at that point of time, the temperature does not change. And that is very critical. And why does this happen? We will explore it in the upcoming slides. And the constant temperature at which this change of phase happens is called its melting point. And if we talk about freezing, it's just the opposite. It is the constant temperature at which a liquid transforms into solid, and the temperature at which this happens is called its freezing point. Now for a pure substance, if I say, then the melting and freezing point, actually it is wrongly written here, incorrectly written, it will be freezing. Let me correct it. The melting and freezing points are identical, and the amount of heat absorbed during melting is same as the amount of heat liberated during freezing. Now let us see the curve, the heating curve when an ice melts. Now here, if I directly move to the curve, then you can see that on x-axis we have time. On y-axis we have the change in temperature. Initially what we had was only ice. When I started to supply the heat to the ice, then although I am supplying the heat, the temperature is not increasing. You can see that from point A to point B, the temperature, the time has passed. It has already passed to 120 seconds. The time has already passed by 120 seconds, but the temperature has not increased by one single bit. And once all the ice gets transformed into water, that means once melting has completed, then only the temperature starts to rise. Okay, so this is what the heating curve of ice looks like. And this phase AB, states that the melting is ongoing. From point B onwards, the phase BC states that all the ice has melted and now we only have water, and this water will then gain energy and this will lead to an increase in the temperature. Now the question is, if heat is being supplied continuously for somewhere around 120 seconds, then where does this heat go? In fact, this heat is called latent heat, which we will study in the upcoming slides. So let us move forward. Now, we have factors which impact melting. First factor is volume. We know that when a substance melts, the volume generally, what happens to the volume? It generally increases. But here we have an anomaly. When it comes to water, and when water melts, initially, upon at 0 degrees Celsius, of course it happens at 0 degrees Celsius, we know that. So at 0 degrees Celsius, when water melts, instead of increase in the volume of the melted water actually decreases. In other words, the density or the volume of ice is more than the volume of water at 0 degree Celsius. Next, when it comes to the impact of pressure, that how pressure impacts the process of melting, then there are two phenomena, two things that you have to keep in mind. There are some liquids, there are some solids, I would say, which contract on melting, for example water, and then there are some solids which expand on melting. Generally there are multiple examples of it. So if, let us say, I have a solid which contracts on melting, then for those, if I increase the pressure, it leads to a decrease in the melting point of that substance. For example, for water, if I increase the pressure, then it leads to a decrease in the melting point. Now the melting point becomes much lower. It goes below 0 degree Celsius. When it comes to other substances which expand on melting, then increasing the pressure leads to an increase in the melting point. Next we have impurities. Impurities have a general impact on all kinds of solids. If you have impurities, then it generally leads to a decrease in the melting point of the substance. Let us move forward And now we are going to talk about vaporization or boiling. Now, the change from liquid to gas phase on absorption of heat at a constant temperature is called vaporization or boiling, and the temperature at which this happens is called the boiling point. Again, it is understandable. Boiling, if I take the example of water, then we know that boiling happens at 100 degrees Celsius. And when the water is boiling, that means it is a phase, it is a I would say a transition phase when the water is actually getting converted into gas. And at that point of time, the temperature of boiling water does not change. It remains constant at 100 degrees Celsius. Again, the question arises, where does the heat, excess heat go, which I am continuously providing to boil the water? This heat is called the latent heat, and it goes, in simple terms if I say, and in fact based on your previous understanding that what you have studied in the last classes, you can say that this heat goes to overcome the force of attraction between the particles, so that the particles of water gets converted into particles of gas. Okay, now for pure substance, again same as melting and freezing. For pure substance, the boiling point and the condensation point are identical. That means boiling water, or you can say steam, condenses at 100 degrees Celsius, and water also vaporizes at 100 degrees Celsius. Now let us move forward. Heating curve for water. Now here we have the heating curve for water. So the system here is that I have water, not ice. Okay, I have water and I am heating it. Then we will understand what happens during the initial phases of heating and what happens when the water reaches its boiling point. So this graph can actually help us to understand that. In the initial time period, at least for the first 30 seconds, you can see that the temperature of liquid, or for example water, in this example, increases from 20 degrees Celsius to 100 degrees Celsius. And after that, it stagnates. It is not changing. So this phase AB states that the water is in liquid form and it gains energy. Whatever the heat is supplied, it gains energy to increase its temperature. Now once the temperature reaches 100 degrees Celsius, which is the boiling point of water, the temperature stagnates and the excess of heat that is being supplied to the water, it gets used up to convert the liquid water into gas. Now we are going to understand the factors that affect boiling. First is volume. We know that when we boil something, the volume of that substance increases. Next we have pressure. Now pressure has a direct dependence. If we increase the pressure, then the boiling point generally increases, and if we decrease the pressure, then the boiling point decreases. So can you please tell me in the comment section again, what will happen if I heat, if let's say if I want to boil water at Mount Everest, let us say, for example, at a height of 5,000 meters from the sea level. What will happen to the boiling point of water? Please do mention it in the comment section. Now let us move forward. What impurities will do? Again, impurities have a direct impact. If we have impurities in a liquid or in a substance, then its boiling point generally increases. So it means salt water will boil at a higher temperature compared to pure water. Now let us move forward. Next, we are going to understand latent heat and specific latent heat. In fact, this is the reason that the heat that we were talking about, where does this excess heat go? Because we were continuously supplying heat to water, or let's say ice, but we did not see any change in temperature when the phase was changing, when there was a change of phase taking place. And this heat was used actually to overcome the force of attraction between the particles so that they can change its phase, and not to increase the temperature. So what is latent heat? If I say latent is the amount of heat supplied to a substance to change its phase, be it from solid to liquid, from liquid to gas, gas to liquid, or liquid to solid. Now next, what is specific latent heat? Specific latent heat is the amount of heat supplied per unit mass of a substance to change its state from, again, solid to liquid, or liquid to gas, gas to liquid, or liquid to solid. Okay, now these two, latent heat and specific latent heat, they have a lot of similarity in between them, if I say so. And that similarity is actually, I can give an analogy here to make you understand what is latent heat and specific latent heat. So you can say that the relationship between heat capacity and specific heat capacity is similar to the relationship between latent heat and specific latent heat. In fact, in case of latent heat, we are not talking about the mass. of the substance that we have. We are only talking about the amount of heat that will be supplied. Now we know that this latent heat in that case will become variable. If I have 2 kg of water, then the latent heat will be more compared to a situation where we have 1 kg of water. But specific latent heat becomes a characteristic property. It simply tells us how much heat energy will be needed if I want to, let's say, boil 1 kg of any substance. Now mathematically, specific latent heat is given as Q divided by M, where Q is the latent heat and M is the mass of the substance. And for pure substances, the specific latent heat of freezing is same as the specific latent heat of melting. That means if I have pure substance, then of course if it is water, then the amount of heat energy supplied to convert ice to water will be same as the amount of heat energy released, or you can say extracted from water to convert it to ice. Now let us move forward. Next, latent heat can be of the following types. In fact, these are some basic definitions according that is given into your curriculum. First is specific latent heat of fusion, which we also call the specific latent heat of melting. Then we have a specific latent heat of vaporization and a specific latent heat of freezing. Now what is a specific latent heat of fusion? It is the amount of heat energy required to melt 1 kg of a solid into its liquid phase. Then what is latent heat of vaporization? It is the amount of heat energy required to convert 1 kg of liquid into gas. And then what is the specific latent heat of freezing? It is the amount of heat required to convert 1 kg of liquid into solid. Now the specific latent heat of freezing again. Now let us understand the latent heat using the kinetic model. Now this is something which I have already told, in fact twice in the previous slides. I will just reiterate it. In fact, if you read it, you will understand that I have already told it in the previous slides. So we know that when the phase transition takes place, at that point of time, the total energy, average of the total energy does not change. In fact, what changes, so the heat that we are supplying at the boiling point, or let's say at the melting point, or during melting or during boiling, the heat that we are supplying, it actually gets used up to overcome the force of attraction between the particles. We know that solids have the particles of solid have a large force of attraction, and hence they are held together. Now if I supply this heat, it does not increase the energy, overall energy of the system, of the solid. Rather, this heat energy gets used up in increasing the space between the particles. And how do we increase the space between the particles? By overcoming the force of attraction that exists between two particles of a solid. Okay? And this heat energy gets actually used up in overcoming this force of attraction. It is not increasing the total energy, that is the sum of kinetic and potential energy. And we have studied in the last video, in the last lecture of calorimetry, that thermal energy or heat energy is nothing but the total kinetic and the sum of total kinetic and potential energy of the molecules of the particle. Now since the average overall, on an overall basis, the total energy is not changing, that means the sum of potential and kinetic energy is not changing, hence the temperature of the system will not change. But since I have to overcome the force of attraction between the particles so that a liquid gets converted into gas or a solid gets converted into liquid, the heat energy gets used up. So that was all for this chapter, guys. I hope you have understood the concepts, and now I think you will have very little doubts left with this chapter. In fact, this chapter is not too much complex. The most important thing, which I iterated at the start of this discussion also, that you will have to solve a lot of numerical questions. A lot of different categories of numerical questions can be formed from the concepts that we have studied in this chapter. So practice a lot of numericals, and if you have any doubts, any queries related to any concepts that we have discussed in this chapter, feel free to ask it in the comment section. We will answer it. Thank you. And one more thing before leaving you guys, I want to say if you enjoyed this video, then please do like, comment and subscribe to our channel, MidhaGuru.